All right, this is for physics CP students way back in November, due November 8th. I'd assigned a homework worksheet called Collisions and Conservation of Momentum. I wanted to debrief you about the last two problems on that homework assignment, starting with problem number 9. It read, identical twins Kate and Karen are rowing their boat on a hot summer afternoon when they decide to go for a swim. Kate, whose mass is 45 kilograms, jumps off the front of the boat. So here's a diagram I've started already. Boat, this must be Kate. She has a mass of 45 kilograms. And she jumps off the front of the boat at a speed of 3 meters per second. Karen, and because they're identical twins, you infer that she is also 45 kilograms. Karen jumps off the back of the boat at a speed of 4 meters per second. If the 70 kilogram boat, if the 70 kilogram rowboat is moving at 1.00 meters per second, when the girls jump, what is the speed of the rowboat after the girls jump? Okay, so here you can see a sketch of the problem. 70 kilogram rowboat, 45 kilogram Kate, 3.00 meters per second. And this is a judgment call, but I'm going to say relative to an inertial observer watching things from outside. So it's not 3 meters per second relative to the moving boat. It's 3 meters per second relative to the shore. Same thing for Karen on the back. 4 meters per second relative to the shore, not relative to the moving boat. We're going to solve this problem using conservation of momentum, hence the idea that the title of the worksheet was Conservation of Momentum. Before either one of them left the boat, we had a total mass of the boat and each of the twins, 45 kilograms and 45 kilograms, is 90 kilograms. So the total mass was 160 kilograms of the boat and the two twins moving at 1 meter per second. Momentum is mass times velocity. If the total mass is 160 kilograms and the velocity is 1.00 meters per second, hopefully you don't need a calculator to figure out that it's 160 kilogram meters per second of momentum. In this physics problem, we're ignoring all the friction of the water. We're ignoring all the friction of the water and treating this as a closed, isolated, frictionless system. Great. That means momentum is conserved. If one twin jumps at 3 meters per second forward and the other one goes 4 meters per second backwards, that is indeed equivalent to one person just going backwards, excuse me, at 1 meter per second. But let's say that you aren't mathematically sure that you could do it that way. In that case, treat it as here's the before situation. The after situation has to work out to the same total momentum. That's the idea of conservation of momentum. The sum of all the momentum before they jump off the boat is equal to the sum of all the momentum after they both have jumped off the boat. So doing it, broken apart into 3 steps or 3 pieces, we have 45 kilograms on the back of the boat. So that's going backwards minus 4 meters per second, plus the twin going off the front of the boat. That would be 45 kilograms times 3 meters per second, plus the mass of the now empty boat times the final velocity of the empty boat. There's only one unknown in this entire expression, and that is the final speed of the empty boat. Well, I'll do it with a calculator. I have negative 180 kilogram meters per second plus 135 kilogram meters per second plus 70 kilograms times the final velocity of the empty boat. By conservation of momentum, these three terms have to add up to a total of 160 kilogram meters per second. All right, so I would add 160 on the right, and to that I would add 180 from the left, bring it to the right. Then I would subtract 135 from both sides. That gives me a total on the right of 205 kilogram meters per second. Next step, divide both sides by the mass of the empty boat to isolate the answer, the final speed of the boat. 205 divided by 70, beep, 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 beep. The calculator says 2.928571429. Looking at the original problem, I recognize there's only one significant figure in the mass of the boat. And I have asked you in general, please don't, please override the sig figs on some of these handouts because the person who typed them up didn't follow the rules of sig figs. So to two sig figs, the answer would be 2.9 meters per second. And if you carried out the 3, you would round off the 8 on the fourth digit to make the third digit a 3. So if you wanted to go as far out as 3 sig figs, the answer to problem number 9 is 2.93 meters per second. I was expecting you to write 2.9 meters per second. Many of you somehow came up with 2.4 meters per second, maybe by nefarious means. Problem 10. A 0.10 kilogram piece of modeling clay is tossed at a motionless 0.10 kilogram block of wood and sticks. The block slides across a frictionless table at 15 meters per second. Hooray! At what speed was the clay tossed? So we're pretending that this is not projectile motion here. We're pretending that this is one-dimensional motion, which is crazy. The mass of the clay and the mass of the block are identical. Of course, they have different densities. Here is the block, and the clay is, I guess I'll draw it as a circular blob, although that doesn't really, we don't know what it's like. It doesn't matter. It's just a point object. They both have identical masses, 0.15 kilograms, 0.15 kilograms. Initially, the block is at rest. So this is the before sketch. Afterwards, the block has the clay stuck to it, and they are both moving off at 15 meters per second. Before, after. This is a one-dimensional, perfectly inelastic collision. Therefore, to use conservation of momentum, the total momentum before they collide is equal to the total momentum after they collide. Well, after they collide, their combined mass is 0.30 kilograms, and they're moving at 15 meters per second. Momentum is the product of mass times velocity. So if you want to do it with your calculators, fine. 0.3 times 15 is, excuse me, 4.5 kilogram meters per second was the momentum before, I'm sorry, after they collided, not before, after they collided, 4.5 kilogram meters per second. That must be equal to the total momentum before they collided. Before they collided, the block of wood was at rest. Its velocity was zero. Therefore, its momentum was zero. Therefore, all of the momentum was in the form of the clay. This is all part A, by the way. So 4.5 kilogram meters per second is the product of this 0.15 kilogram block of modeling clay times its initial velocity. There's only one unknown in this problem, and you solve it by dividing 4.5 by 0.15, and beep, 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 you get an initial speed of the modeling clay of 30 meters per second. Many of you got the correct answer for part A. Many of you got the wrong answer for part B. This is why I'm debriefing you on problem 10. Here's where lots of students failed to get the correct answer. Part B, the clay is replaced with a bouncy ball tossed with the same speed. And when they say with the same speed, they mean now that you've figured out that the initial velocity of the clay was 30 meters per second, that is the initial velocity of the bouncy ball at the beginning of problem part B. I'm now rereading resuming reading the question. The bouncy ball rebounds from the wooden block at a speed of 10 meters per second. So afterwards, the bouncy ball is rebounding. That means it's going to the left and it's going at 10 meters per second. Many of you just didn't read that correctly, or one person read it wrong and the rest of you followed along. What effect does this have on the wooden block and why? Okay, when we ask you some question like this, what happens? We really want you to include quantitative calculations to support your answer. We don't want you to just say, oh, it's going to bounce the other way or faster. We want you to tell us how fast it's going to go. So before, we had this wood block. And by the way, when they say the clay is replaced with a bouncy ball, it's presumed that the bouncy ball has the same mass as the clay that it is replacing. It doesn't say that explicitly. And in fact, this problem does violate conservation of kinetic energy, which could be explained if the mass of the bouncy ball were different from the mass of the clay. But we're going to solve this problem simply using conservation of momentum while making the assumption that the bouncy ball has the same mass as the clay. Okay, so here we go. The wood block is going to recoil off to the right afterwards. Before situation, after situation. What's significant is the change in velocity is negative 40 meters per second here. If it's going 30 to the right and it bounces 10 to the left, it has to slow down by 30 and then increase by 10 in the opposite direction. That's a change of negative 40 meters per second. The change in velocity of the identical mass wood block has to also be 40 meters per second. So the final velocity of the wood block is 40 meters per second. Very, very few students came up with that answer. This ends my debrief